Hi, I am Bhavya and I am presenting our work Loop, looking for optimal hard negative embeddings for deep metric learning. Consider the problem of deep metric learning, where the input samples are first projected to the embedding space using deep networks, and then we use some objective to train them so that the samples from the same class, known as positives, move closer and the samples from different classes, known as negatives, move farther away, as shown in this figure. One such objective is the triplet loss, which is formulated using the distances between the positives and the negatives. Using such an objective for training is not always effective. If the embeddings satisfy the objective, the loss function and the resulting gradients are small, leading to slow learning. To improve learning, we can use hard examples. As shown in the figure, negatives which lie close to the positives and violate the training objective are hard negatives which can benefit learning. To find such samples, hard negative mining and generation based methods have been proposed. Mining based methods look for the most informative samples in the dataset and rely on them for training. Generation based methods employ a generative model to generate synthetic hard samples not already present in the dataset. Both these approaches face some drawbacks. Mining based methods rely on a subset of samples, making them prone to learning biased mappings, leading to poor generalization. Generation based methods lead to harder optimization and increase in model complexity as they need another model. We propose to look for optimal hard negatives directly in the embedding space to exploit the best of both worlds. Our approach considers all samples and avoids biased learning. It operates in the embedding space, so it doesn't increase training complexity or optimization difficulty. And it can be combined easily with existing metric learning based losses. To understand how loop works, let's see an illustration. We have two pairs of points in the embedding space. We obtain the curves joining them so that the points lying on the curves belong to the same class as that of the endpoints. Our aim is to find synthetic samples lying on these curves which minimize the distance between them. These samples then act as the pair of hard negatives we need for the training objective. Next, for the mathematical formulation, consider the notation shown in this figure. Our objective is to minimize the distance between the synthetic samples P1 and P2. To do that, we proceed as follows. First, for each pair of samples, we apply Gram-Schmidt orthogonalization to obtain the basis vectors for the space they span. Next, we rotate the samples along the curves to get the points P1 and P2. Finally, we aim to minimize the distance-based objective shown here. This forms a constraint optimization problem as the synthetic samples should remain between the endpoints of the curves. This can be solved using the KKT conditions, the details for which can be found in the paper. Finally, we move on to the results. We evaluate our method on three benchmark datasets for clustering and retrieval tasks. This slide shows comparison with various generation-based methods. It can be seen that combining loop with various metric learning based losses leads to an improvement over the baseline loss as well as over other generation based methods in most of the cases. This slide shows comparison with various sampling based methods. Clearly, our method performs better than the other methods for all the cases. For more details, please visit our GitHub link.